So it looks like you guys beat the other section, I think, for the first time. We got more people here today. So I know that yesterday there were a couple issues with Canvas, but hopefully we don't have any of those kind of moving forward. There's like a couple hours where you may not have been able to access it yesterday afternoon, but nothing was kind of taken off of there and everything kind of showed up okay. So I think we're good. It didn't really affect us. Affected me a lot yesterday with my other classes, but we're a little bit lucky, I guess. So today, where are we? We're going to pick up where we left off. I'll kind of do a little bit of review of these conditional probabilities, and then we'll jump into using this union data file, and we'll do quite a bit of Excel work. Okay? So we left off thinking about these conditional probabilities, right? And we had this multiplication rule where we said, if I want to find a conditional probability, it's just take the intersection of those two events and divide by whatever I'm conditioning on, whatever I'm given, or whatever's in that right-hand side of that line. Okay? So we looked at this example in the contingency table. Oh, I had this up there for the last class. Let's how can I do this? I can actually add in this. So let's do this for now. We'll go back here. So this is what we had last class. So we said, given that I know C2 has occurred, what's the probability R1 has occurred? So we could rewrite that as the intersection of those two things divided by the probability of C2, what we were conditioning on. Okay? It's very easy then to go get the intersection of, R1 and C2, which is 0.2. Probability of C2, we go down to the total, 0.5, and it's kind of where we ended up. So what we were thinking about there is, it was almost like, if I don't condition on anything and I just want to find just the probability of R1, the unconditional probability of R1, I just go over the total, right? If I imagine I have this huge experimental outcome space that has an area of 1, and of that area, 0.6 of it are outcomes that are in R1, okay, in that event. Once I've conditioned on C2, I'm no longer looking at the entire experimental outcome area. I'm only looking at half of it, right? And of that remaining half, how much of that remaining half is in R1? Well, if I look of that remaining half, 0.2 of that 0.5 area is in R1. And that's essentially 0.2 out of the 0.5 area is how we're getting that conditional probability. Right? We've limited the space we're looking at down to a smaller subset, but it could be once we've limited it down to this smaller space, more of that space is made up of R1 than when we're looking at the entire experimental outcome space. Now, it could be less, could be more. Right? So let's think about instead, if I did this, look for the conditional probability where I said, given that C1 has occurred, what's the probability that I see R1? Right? So I'm still looking at a conditional probability of R1, but I'm conditioning on something else. Okay? Well, I can rewrite that as the intersection divided by whatever I'm conditioning on. I can get the intersection of R1 and C1 is 0.4. The probability of C1 is 0.5, and I can compute that conditional probability. But what this is really telling me is, well, look, if I'm not conditioning on anything, 60% of that space is in R1. However, if you tell me that C2 has occurred, I said that I'm limiting the space I'm looking at to just half of that area, so 0.5. And of that 0.5 area, 0.2 is in R1. But if I condition on C1, it still limits the entire experimental outcome space down to an area of 0.5. But of that remaining area of 0.5 that's in C1, 0.4 of it is in R1. So knowing that C1 has occurred, it's much more likely that R1 has also occurred, right? Then if I'm thinking about if I tell you C2 has occurred, it's not near as likely, right? Only half as likely, or probably is half as large. Okay? So this is kind of a review of how we find these conditional probabilities, kind of what they represent to us. And what we're really thinking about here is like having this additional information really allows me to update my probability of whatever event I'm interested in. So we're going to look at a definition with this in mind, which is if events are independent. Okay? So we said that two events are independent if this unconditional probability of A, right? We're not conditioning on anything. We're just kind of think about it as like the normal probability, right? Normal probability of A. If that is equal to the conditional probability of A, right? We're still looking for the probability of A, but we're conditioning on this additional piece of information. If those two things end up being the same, well, that means the additional information was worthless, right? It didn't have any relationship to that event A. So we would say that A and B are independent, because knowing that B has occurred doesn't change the probability that A has occurred at all. Okay? And then kind of we could do the other way as well, right? And the probability of conditional probability of B is equal to the unconditional probability of B. We'd say that A and B are independent. If A is independent from B, B is independent from A in these examples that we're looking at. Okay? So if we go back and think about our multiplication rule, we said we could rearrange the equation a little bit so that I can always find the intersection of two events by taking the conditional probability of an event and multiplying by what I'm conditioning on. Right? However, if events are independent, what could I plug in here instead of the conditional probability of B? Well, if they're independent, that conditional probability should just be equal to the unconditional, just the probability of B here, which gives us this kind of simplified formula, right? So if we have two events that are independent, finding the intersection is a little bit easier in that we can just take the probability of each event and multiply it by each other. Okay? And I'll talk through this a little bit more in a second with some examples. But with this definition of independence in mind, and kind of as kind of a byproduct of two events being independent, is that this equation should also hold, right? That the intersection of two events is just the product of the probability of each event, right? Or each event multiplied by each other. The probability of each event multiplied by each other. So if we look at a contingency table, right? What's the probability of A from this table? It's just I can wait through awkward silence. If I want the probability of A, what's the probability of A here? Yeah, go over to the total column, 0.6. Right? So this, the probability of A is 0.6. Let's find the conditional probability of A. If it is equal to 0.6, we would say these events are independent, right? Having this additional piece of information didn't influence the probability of A at all. So I rewrite that conditional probability using my multiplication rule, that it's the intersection of the two events divided by the probability of what I condition on. The intersection of those two is 0.15. The probability of B here is 0.25. Right? We can put that in our calculator, we end up getting 0.6. Sure enough, that's the same as the probability of A. We'd say these events are independent. Okay? You can kind of think of, you can kind of think about being independent as, let's say I'm thinking about eye color, and I say the probability that someone has blue eyes is 0.1. Right? Now I give you some additional information. I say, okay, what's the probability someone has blue eyes given that they're, I don't know, over 6 feet tall? That, I don't know, what does that being over 6 feet tall have anything to do with having blue eyes, right? It's still probably 0.1, right? If I took all the people over 6 foot tall, my guess is the percent of people that have blue eyes in that population is the same as the population as a whole. That event B had nothing to do with A. It was independent from A. Right? So that's kind of the idea of what we're checking for there. We could have also checked it using, seeing if the conditional probability of B was equal to the unconditional probability of B. And if A is independent from B, B should be independent from A. So we'll go ahead and check that. The probability of B here is 0.25. Rewrite that conditional probability of B. It's the intersection of those two divided by what we're conditioning on. So the intersection is 0.15. Probability of A is 0.16. Sure enough, that conditional probability of B is the same as the unconditional probability of B. So it didn't matter which way we used to check that, we would have found they're independent either way. Okay? Any questions on this before we keep moving? Yeah.
Are there any situations where one variable would be independent and the other one is dependent on the other variable?
So when we're talking about independence, think about this as the relationship, we're not trying to identify like which direction the relationship is. Like it's not like A is a function of B. We're not talking about that. That very well could be that A is a function of B and B is not a function of A or something like that. But here, when we're thinking about independence, it's whether or not the probabilities of these things occurring are independent. So it'll never be the case where if A is independent from B, B will be independent from A. And the next check, I think, will hopefully kind of show why, because there's no way we could check it in two directions. So remember, I said if two events are independent, this would have to hold, right? So if the intersection of two events is equal to the probability of those events multiplied by each other, that was a byproduct of them being independent. Well, here there's no way, if I'm checking this, there's no way I could check it differently for the direction of the relationship. So here, if I look at the intersection of A and B, that's 0.15, and then take the probability of A, 0.6, times the probability of B times 0.25, which ends up being exactly the same. Right? So this check kind of maybe helps us remember that if A is independent from B, B is independent from A. Like these two things are just independent from each other. These events. Right? And this is where like I'm using kind of using variables to check for this, or the way I'm talking about it, it's like variables that we're thinking about that could be independent from each other. But really remember, we're thinking about experimental outcomes. So it's like the outcomes, the probability I see an outcome in A is independent from seeing the probability of seeing an outcome in B. Yeah. Yeah, so let's say we went through and computed this and it was 0.3. Well, that's not the same as the intersection, so we would say they're not independent, or I guess you could say dependent, right? If we want to think about it that way. Any other questions on this? These are good. Okay. So we really just went through three ways we could check for independence, right? We could check to see if this holds, or we could kind of use the more definitions of these and then kind of use our contingency table to check it. And I put up here, I won't ask you like a question in this or necessarily like on the exam or anything, but one thing that I want to mention here, and I'm not going to go deep into the thought process. I might give an example here where I could relate this to it, but if two events are independent from each other, what ends up being true is the complements are also independent. So notice here, if I take A complement, probably the A complement and probably the B complement, I get 0.3. That's actually the same as the intersection of the complements. So if two events are independent, their complements will be as well. So think about it this way. Use the example last class. I think I like it. So let's say event A is that I have blue eyes, and event B is that I'm a registered Democrat, right? Well, those two things, if we use these probabilities, they're independent from each other, right? The probability someone I choose at random has blue eyes is the same as the probability that someone has blue eyes if I know that they're a registered Democrat. There's no eye color kind of differentials across the political spectrum. So if those two are independent, their complement should be as well. So not having blue eyes, right, having an eye color that's not blue, should be independent from being a registered Republican, right? The complement, if we think about there's only, let's assume there's two political parties for the sake of this example, right? So those complements, not having blue eyes and being a registered Republican, would also be independent. And that's kind of the idea that if two events are independent, their complements will be as well. So technically, there's a fourth way we could check. Right? If we wanted to check the complements first, that would also work. All right. So let's use this idea of independence and see how it kind of gets applied to some real situations. So I put here, so think about this as a Kenny Rogers or the Gamblers Fallacy, right? So we'll start out with this scenario. Think about if I flip a coin, what's the probability it comes up heads? 50% or probability of 0.5. Right? If I keep flipping a coin enough, like let's say I flip it 10,000 times, I know that if I were to count the number of heads out of 10,000, it should be right around 50%, right? Maybe a little bit off, but if I could do an infinite number of coin flips, I'd see 50% come up heads. So because I know that in the long run, it kind of hits this 50% mark, what we see a lot of people is fall victim to a fallacy. So if we remember that each coin flip is independent, right? So I flip a coin, I see some, heads or tails. I then flip a coin again. I see either heads or tails. Do you know, like, at what point, right, am I going to start to maybe fall victim to this gambler's fallacy? So if I say I saw 9 heads come up in a row, right? I know it's a fair coin, but I see 9 heads come up in a row. What might I be, what would the probability of seeing a heads on that 10th coin flip be? 50%, right? But what you can fall victim to is if you know that in the long run, they have to even out. Some people say, well, if I see 9 in a row, I know it has to balance out, so like it has to be tails, right? Well, no, each one's independent from each other, right? So the probability is still 50%, right? Doesn't matter how many consecutive heads you see in a row, the probability you get heads on the next coin flip is always going to be 50%. So you can go through, and I use Excel, I simulated coin flips, and you can kind of look at, these are essentially conditional probabilities. Conditioned on seeing just 1 tails prior, what's the probability I see heads on this coin flip? 50%. If I look at all the scenarios in that simulation where I saw previously 2 consecutive tails, what's the probability the next coin flip was a head? 50%. What about the times where I saw 3 previous tails or 4 previous tails? What's the probability I see a head on the next flip? It's always 50%, right? Kind of floating really, really close to that 50% level. So it doesn't matter, right? If we condition on the outcomes of the previous events, it doesn't influence the probability of the current event at all because they're independent, right? Each one of these conditional probabilities, if the current coin flip is independent from the previous coin flips, all these conditional probabilities should be the same as the unconditional probability, just the probability of getting a heads, which is all 0.5, okay? So we see people fall victim to this, though, a lot, where if they see a long streak of consecutive outcomes the same, they think that the other outcome, right, has to be more likely, or that the probability has changed, which is not true. And in fact, there's a good example. So if we go back, what was it, 1913, if we have a roulette table, basically you can think about it as if I spin it, there's a 50% chance this little ball lands on red, and there's a 50% chance this little ball lands on black. I know there's a green space, but for the sake of this, think about it, it's just the same thing, right? So that's really close to 50% each. So there's this one instance, they spin this wheel and it comes up black 26 times in a row, okay? Well, after like the 15th time, probably earlier than that, right? Like after the 10th time, seeing 10 black spins in a row, people start to think, well, this has to balance out to 50%, so the probability it's going to come up red on the 11th spin, much higher, right? So people start putting their money on red. Well, it comes up black again. Well, 11 times in a row, for sure it has to balance out on the 12th. Everyone bet on red, black hits again. This kind of continues up to the 26th time, and this casino made like a millions of, I guess what, not dollars, francs here, right? So, you don't want to fall, if they're independent events, you should have been betting as though it was a 50-50 bet every single time, right? Another one, I might waste a little time, but I have a sports econ course, but I was getting interested in sports betting for a while. And when you look at it, all the lines that they set, like the Super Bowl is interesting. They have like lines set for everything, but every bet is meant to be a 50-50 bet, right? So anytime they set a betting line, it's so that it should be like a 50% chance that it happens one way or the other. But what people will do is they'll see something that covers the spread or like that, they say it, and they'll think, well, if previously, the outcome was this, it has to be more likely we see it in the future. Well, no, right? Each time they set one of those betting lines, they're all independent. So each bet should always be a 50% chance that you win and a 50% chance you lose, unless you know something that these huge organizations that are setting these betting lines and have a lot of interest in doing so, you have some information that they don't, which I guess, I don't know, what's the guy that was streaking in the Super Bowl? Apparently he had more information when I don't know if you've heard the story. He bet on himself, basically. So, but that's the idea, right? We can see this play out a lot in gambling behaviors, okay? So, I think here, we'll go out and we'll start doing a little bit of work in Excel, okay? So we have these contingency tables. We've thought about these different things. Oh, actually, before I go to the union example, I want to do a sheet and point this out. I think there's one, on the next Connect homework, I might have a question that we have to think about this. So, if I think about the probability that a coin flip comes up heads, it was 0.5. Or we could think about it as that example with the roulette table. I don't know, the probability it comes up black is 0.5. Well, what's the probability that it comes up black on the first 2 spins? Right? So the first spin of the roulette table it lands black, and the second spin it lands black. Well, if they're independent events, we said the intersection of those 2 things should just be the probability of A times the probability of B. So the probability it comes up black on the first spin and on the second should just be 0.5 times 0.5. Right? And what about the first 3 spins? 0.5 times 0.5 times 0.5. 4 spins, so on and so forth. What's the probability that they saw 26 come up black in a row, which is what ended up actually happening? Well, it's basically 0.5 times 0.5 26 times, or 0.5 to the 26th. So anytime we have these independent events like flipping coins, and well, how likely is it if I flip a coin 10 times that I get 10 heads in a row? Well, you basically just take that underlying probability, and if the events are independent, you can raise it to the power of however many times you're interested in seeing that outcome in a row. So coming up black 26 times in a row, move the decimal point 8 places to the left, so 0.00000001. What's the probability of seeing that occur? Or pretty much, it was very, very, very unlikely. Right? We're starting to talk about like lottery level chances here. So I kind of want to point that out. That definition of independence kind of helps us out with examples like that. So with this idea of independence in mind, we're using these contingency tables that I showed you. They were kind of like toy examples. Where was I getting the numbers from? Who knows? But you actually, more often than not, will build your own contingency table, right? Those probabilities you're going to derive from some data, empirical assignment, right? We talked about empirically assigning them. So I have this data set, and it's got all these different industries in different time periods. It has what their percent of workers that were union members in that industry in that year. It has union member weekly earnings, and it has non-union member weekly earnings. I then created this variable, which was, well, what's the difference between union and non-union earnings, right? So, for example, in the accommodation industry in 2008, about 8% of their members were in the union, and the difference between union weekly earnings and non-union weekly earnings was about $111, right? So we're going to use this and start to think about, we could look at probabilities to understand what the relationship is between union membership and kind of how much more money the union members can earn. Think about it this way. If I have an industry that's 100% of union members, that union has a lot of bargaining power because I can't go out and hire non-union people. So I'm going to be able to drive that wage up a lot higher if 100% of the workers in the industry are union. If there's only like 1% of the workers in that industry are in the union, when the union tries to bargain for higher wages, what do you think the companies do? Well, there's 99% of the other workers that I don't have to worry about paying higher union wages, right? So the union member, they can't bargain for as great of a wage differential, right? So we're going to look at that relationship between union membership in industry and the difference in union, non-union earnings. So I go over here. I could find the averages here. So this was just, I probably shouldn't even waste time with this, but we'll go over here, take the average of our union member earnings, so control shift or command shift on a Mac down arrow. You get the average, 10% in the union. Union earnings was in, I think it's this column. Non-union earnings was in this column. And then I can kind of look at that average difference. Yeah, so when I just want to select that real quick, I've got my function, selecting the very first observation, control shift or a Mac command shift, and then hit the down arrow. And actually, if I want, in this situation, we're only selecting one variable, but that's also like a really useful tip. Like let's say, I'm glad you asked this. Well, now I messed up this all up. It's okay. Let's select this and then I'll show you the useful tip. So control shift or command shift down arrow. So let's say I want to go just to the very bottom of my data set. If I'm not putting a function in, I hold Control Shift. I can go all the way down to the very bottom, and then maybe like I want to do some work down here or something. If I had a ton of variables, I could go over to the left by using Control Shift and hitting the left arrow. That sends me all the way over to my first variable. You know, so I can kind of use that to navigate in Excel a little bit easier as well. I know you can use the home key and stuff, but I've just always found that my hands aren't over there on my keyboard very often, so I just use that Control Shift to navigate a little bit. So here's just some averages just to kind of get an idea about the data that we're looking at. So the average kind of differential, wage differential here is about $120. The average membership is about 10%. So for now, we're going to actually kind of create some events using certain cutoff values. So I'm going to use 10 and 100 here. Now, as we work through this, it'll be a little bit clearer why I'm using those values. But what I'm going to define is, instead of having this contingency table that has A complement, B, and B complement, I'm going to create those events. So for my event B and B complement, I'm going to define event B as having 10% or higher union membership in my industry. B complement would then be that there's below 10% union membership in my industry. My event A will be that the wage differential between union and non-union workers in that industry is $100 or more. And A complement is that that difference is less than 100. So I've set this up just like my contingency tables that we've been looking at, but I actually have like names, like real events now. Okay? So what I'm going to do, before I can get probabilities, I'm basing this off of data. So what I'm going to do is think about how many of these industries had union membership 10% or higher and a wage differential of $100 or more. I'm going to count up the number of industries that fit those two events, right, in my data set. Say it's 100 different industries. Well, how can I turn that into a probability? Well, it's going to be 100 out of however many observations I have, right? So it's kind of like when we were doing the frequencies and then turning them into relative frequencies by dividing by the total number of observations. That's what we're doing here, right? It's just that we're not building a histogram, we're building a contingency table. So we're going to use that count ifs formula again. Okay. And the first thing that we want to check is to see, is union membership 10% or higher? So we're going to tell Excel, right, use this count ifs formula, go through this union membership variable, right? So Control Shift or Command Shift, hit the down arrow. Go back up here so I can see it. It's kind of a pain, but so I selected that variable and said, look through that union membership variable and only count the observations that have greater than or equal to that 10% cutoff that I chose, right? So it goes through that variable and counts the industry if it has union membership that's above, greater than or equal to 10%. However, I also only want to count it if the wage differential in the industry is $100 or more between union and non-union workers. So I'll select this difference in earnings variable. Now, what I'm going to do here, instead of like using that Control Shift and having to scroll back up to see the formula, and I usually wouldn't have to do that if I can remember it, but because I'm teaching it to you, I kind of want to show it to you. I'm just actually going to type it in. I think this is actually just easier, especially if you're on a laptop where you're using the mouse pad. Well, I know the range of data now goes from 2 to 736, and I just want to look at this difference in earnings variable. So I'm going to look at that column of H2 through H736. Right, so I'm just using what I already did to kind of type that in there as opposed to selecting it. And you can select it, it just takes a little bit more time and kind of annoying to have to scroll back up. So now I'll put a comma. And what I want to use this variable to check is that variable $100 or greater? So is it greater than or equal to, and then an and sign, is it greater than or equal to $100 differential, right? And then I'd be done. Okay. So I'm going to show you two ways where I can now use this one line that I typed into Excel to kind of save me some time. So the first thing I could do is, let's say I select this and I copy it, and then I'm going to hit enter, so I'm out of the cell now. Well, if I go over here, I'm going to have to use that count ifs formula again, and I'm going to have to count, type everything in again and see is the differential $100 or more, but now I'm checking to see is the membership below 10%. But I basically want the exact same equation. I'm just going to be changing those equality signs. So if I click here into this cell, and now I paste, if I copy paste this way, it doesn't update any of those cell references. It copies it exactly as it was before. So notice I should get the exact same value. And then I could go in, and now I want to check to see, well, now is union membership not greater than or equal to 10? But now I want to know, is it less than 10, right? Below 10%. So the other one, do I need to change the other one? Well, here I'm still looking to see, is the wage differential, yeah. Now when I copy this down one, now I'll have to think about updating the other variable. Yep. So you can do it that way. I think the easier way would be, I'm going to freeze everything in the cell, because no matter which one of these I'm looking at, which one of these intersections essentially, I'm using the same range of data and I'm using the same cutoff value. So I'm just going to go through, and it's really annoying if you try to select this and hit F4 or Command T on a Mac. It's going to yell at you there. You kind of heard that go off. It doesn't like non-cell references, so unfortunately we have to go through and select these individually. Hit F4 or FN F4, or if you're on a Mac, Command T, select these, freeze those, and then finally freeze that last cell reference. Now if I do it this way, now I can just copy over, copy down, and it copies everything exactly the same. And now I just have to go in and update things to fit the row and column headings. So in this one, it was below 10%. We already talked about, so I changed this to a less than sign. But it was below 10% with a wage differential of still greater than or equal to 100. Down here, I want to check to see, is union membership 10% or higher? So I don't have to change that. But now I want to see, well, does the industry have less than $100 wage differential? And then for this one, it wants below 10% and below $100 wage differential. So I'll change both of these to less than signs. Right? So I think that way, by freezing it, it's a little bit easier. Just copy over and down, and then just go in and change those equalities to match your row and column headings. Okay? Yeah.
You said to freeze a cell selection on a
Mm-hmm.
Mac.
Yeah, it's anyone with a Mac here. Can someone verify? That is right. Okay, I always worry that I'm messing it up, but yeah, it's Command T. When you ask me that, then I start to think, oh geez, am I like, did he try it and it didn't work? No, I think it should be Command T on a Mac. I don't think any of the new Macs have like a weird key like the FN that like some of these other laptops do, but yeah, it should just be Command T should work for you. So we got everything working now. We've got our four kind of intersections. They're not probabilities yet. But now we need to get the totals, right? So what's one thing we said with contingency tables? How can I reproduce those total columns? What could I do here? Just add across the rows and down the columns. Why does that work? Well, think about it. The total here should be the number of industries with a wage differential of $100 or more. If I count up the number of industries with a wage differential of $100 or more, and 10% or higher union membership, and the number that have, or the number of industries with $100 or more wage differential, and they have below 10%, well, I've essentially counted every single industry that has a wage differential of more than 100, because they have to belong to either above or below 10% union membership. So if I just add those up using that sum function, that should give me my total, right? And I can do the same thing kind of applies for all these other totals. So I just want the sum function here. So I copied that down. Now it adds up these two for me. Use the sum function, add down the columns, hit enter, drag this over. It updates these for me. So it's adding these two together. And now I've got all my totals. Now, if I add up the number of industries that have 10% or higher union membership to the number that have below 10%, what should those two values add up to? Not a specific number, but what should that represent? Everything. I've counted every industry in my data set, at least in one of those categories, right? So when I add those up, this should represent my total number of observations, okay? So how can I check that? We said there's a way you can count the number of observations, which was equals It's literally in the sentence that I just said. Yeah, it's just the count function, right? So we've got that count function. We'll select the variable we're interested in, Control Shift, Command Shift on a Mac, hit the down arrow, hit enter, and it'll send us all the way back up. So that's kind of nice. Sure enough, we got it right. But this is a good way to check yourself. Like, let's say I forgot the equalities up here in this one. It'd be a few observations off. There must be a few observations that are exactly equal to 10%. So if I mess up those equalities, I would get to this point and say, I made a mistake, right? Because I know this count function will give me the total number of observations correctly. So I must have done something wrong. I go back in, and sure enough, I forgot to include the equalities here. I update it, and now I'm feeling better about it. Okay? So we've got all these frequencies, and I said, just like with histograms, if we want to turn them into probabilities, well, it's basically like saying there's 221 industries that fit this criteria out of 735. So the probability that if I chose an industry at random, it's in this category, or it fits these criteria, would be 221 out of 735, right? Just that frequency divided by the total number of observations. Now, that's going to be the same for each one of these other cells. So I'm going to just copy this over. It would go from K9 to L9. So I want that to reference to update. But I don't want M11 to start moving around, right? I always want to use the total number of observations as my denominator. So I'll go in, freeze that cell reference, right? Now when I copy this over, right, notice here, now it's taking the total for that row heading, dividing it by the total number of observations. So everything's going to work out perfectly. If I freeze that, where I can get all of these probabilities based off the frequencies that I calculated earlier. So this step should be very easy. Once you have those frequencies, the count-ifs formula is probably the hardest part of it. Well, now it's just a matter of dividing everything by the total number of observations. Okay? And I should get 1 here, right? I should always, at this point, I should always be dividing the total number of observations by the total number of observations. So if I get to this step and I don't have 1, I should be concerned. I know I made a mistake somewhere. I'm going to show you this just because I think it's easier to deal with. This, like, I don't know why this hurts my eyes and my brain. There's this option under the Home tab where you can, am I going the right way? Kind of have, it's just changing the display, right? So one thing that maybe on a future assignment you need to be careful of as well. So this just changed what's displayed to me. It still stores the numbers out to whatever decimal we want. And it still uses the numbers as though they're all the way out to the decimal we want. If I wanted to change these to percentages, right, it'll change the way that they're displayed, right? But it doesn't actually store 30 in there. The value stored in there is still 0.3. So if I start to use this, to create variances or things like that, some of the other formulas in Excel will not keep this formatting. And so it'll kind of screw with you a little bit because you'll be like, if you start doing variances where you're squaring things, it's not actually squaring 100, it's squaring 1, right? So we need to be a little bit careful with kind of using these display options, especially if we want to display things as percentages. I often would say, like, kind of stay away from that. So I'm going to actually undo that last thing I did. But in terms of just having the number of decimals displayed changed, I think that's a useful tool, and so we're going to use that. Okay. So once I have this contingency table, now I can start to answer questions that we were doing before. So what's the probability that if I chose an industry at random, it has union membership of 10% or higher? That would just be what? Yeah, 39%, or the probability of 0.39, right? So I'm just going to select that cell. I've got my answer. What's the probability it has 10% or higher union membership and the wage differential is $100 or more? Yeah, the 0.3, right? The intersection of those two events is right here, right? 10% or higher union membership, $100 or more wage differential. What if I want the conditional probability? So given that I know I'm looking at an industry with 10% or higher union membership, what's the probability that the union gets a more than $100 wage differential from non-union workers? We said to find a conditional probability, we would take the intersection of these two things and divide by the probability of whatever we condition on. So actually, let me expand this a little bit so this looks a little bit cleaner. There we go. So the intersection of these two things, $100 or more wage differential, 10% or higher, right here, that's the intersection of those two. Divided by the probability of what we're conditioning on, so 10% or higher, it's right there. And that should give us our conditional probability. Now notice I was using the same thing up here, but I could have asked something, something that didn't match up. So we get about 76% or a probability of 0.76 or 77. What if I want the conditional probability of, given that they have below 10% union membership or low union membership, then what's the probability they can get $100 or more wage differential? Well, that's the intersection of these two events, so $100 or more and below 10%, divided by the probability of what I'm conditioning on, below 10%. Hit enter. So at this point, what this is telling me is that if I know an industry has high union membership, right, 10% or higher, the probability that they get $100 or more wage differential from their non-union counterparts, there's about a 76% chance, or a probability is about 0.77. Yeah. For here? So this is just telling me the probability that they have $100 or more wage differential across all the industries. This is essentially saying, I'm only looking at industries that have 10% or higher union membership. Now, out of those industries that fit that criteria, that have 10% or higher union membership, what's the probability one of them has a wage differential of more than $100, right? And that's going to be higher than the 0.55. Why is that higher? Well, because the higher the percent of union members, the fewer non-union workers I can go out and get. So that union has more power, it's more likely they can bargain for this huge over $100 wage differential, right? As opposed to industries that have below 10%, if you tell me, given that I'm looking at an industry with below 10% union membership, the probability that in that industry they can get $100 or more wage differential, it's only a 40% chance, right? Much lower than these industries where we see higher union membership. Right? So this is just kind of highlighting the idea that we're looking for the probability of the same thing here. They're conditional probabilities though, and when I condition on different events, I may end up with very different probabilities for, if I'm, looking at the same event because I'm conditioning on something different, right? It'd be the same as, let's say I'm interested, if I chose someone at random, what's the probability that they're over 7 feet tall? Very, very low. If I say, what's the probability if I condition on that they're an NBA player, that they're over 7 feet tall? It's increased quite a bit, right? It's not the same as that general underlying probability. Yep, so yeah, if you want to think about these conditional probabilities, you can say, what's the probability of seeing $100 or more wage differential, given that the union membership is 10% or higher. You can read it that way, but I think it makes it easier to think about, given that I'm only looking at industries with 10% or higher. So it's like, I'm now not looking at every industry, I'm only looking at a small subset. And out of those remaining industries, now what's the probability that I see them have more than 100? Yep. Yeah, those are good questions that kind of clarify this. Any other questions on just kind of the Excel portion of this? We're okay with this? So I want to mention a couple other things here. One, I tried to use these cutoffs to be around the averages. So you can kind of think about this as, if I have above average union membership, what's the probability I have above average differentials? But you could play around with this and you're like, well, I just don't want above average. I want like, what if you have to have like really high, like above 20%? I want to use as my cutoff. Now, it doesn't change my labels, but all my numbers update, right? So all of my numbers updated here when I change that from 10 to 20. And notice we get different values out here for our conditional probabilities. I could also up here, instead of using a value, if I didn't use these cell references in my count ifs, then when I go back in here, I'd have to like change 10 in every single cell and redo all my work. But if I use these cell references, whatever I do to this cell, it just automatically updates everything. I could also, instead of looking at like 100, I could say, well, what about above or below the average wage differential? So instead of 100, I could do, well, I want to find the average of this difference variable, and I'm going to use that as my cutoff, and everything would update there as well. Now, I think what I'll do, I'm going to post an additional file up there just to kind of look at. So this is the union data file. I have this old one. I don't really like the example as much anymore, but it's got kind of the blank file, but it also has the finalized with like all the work where we're looking at, this is really big, so let's change this. Where it's got like drug use and then this like, it's kind of like an IQ with an ASVAB military, it's used primarily test in the military, but it tries to measure aptitude, but you can look at like different cutoffs here. Now here where it was like never use cocaine or used, notice I'm like using 1 as my cutoff, right? If you're 1 or higher, if you ever used it was a 1, if you never used it was a 0, right? So it's just another example you can kind of look at. But this is the one they worked through in class, this union data. If you're kind of, once we get to the next Excel assignment, you can kind of use this as your template for parts of it, okay? Any questions? You want to see another cell again, or we're okay with this? Yep. Yeah. So this is actually, yeah. So this is actually already on Canvas, and I should have mentioned this. I started on the blank worksheet. Notice there was a final complete one, and it basically has everything that we just did. Yep. They might be in slightly different cells, I think, than I ended up right. Like I think I had 110 right next to each other, but yeah, everything kind of the same. Notice we have the same values down here. So. Yep. So that's already up on Canvas in the in-class data folder. So I want to, a couple minutes. I do want to introduce this idea before we get out of here. So Bayes' theorem, which we're going to do on Friday and probably even spill over into Monday. The whole idea of what we're doing is basically there's an underlying probability of something. So like maybe I say if I don't think anybody in this world, no matter who you select at random, can dunk on a 12-foot rim. Maybe I think that. Someone then, we run the experiment, and at some point there is someone who actually is able to do that. Well, now I have to update my probability. I now no longer think the probability is 0. I think that it's something slightly above 0, right? So we're going to be using the outcome of a test to update our probability about whatever we're interested in. So the way that we're going to set this up, and I'll review this a little bit more on Friday, we're going to have 2 underlying states of nature. So I'll go through these other examples, but imagine it's like having a disease or not. So maybe having COVID or not having COVID. There is some true underlying state of nature when you look at someone, whether they have it or they don't. Now, I don't think anyone can just look at someone and know. So we run a test, right? There's 2 outcomes of the test, right? We're going to kind of ignore kind of one of these disease ones where you can get inconclusive. We're going to say we run the test till we get a result. We either see positive or we see negative, right? Now, if I see a positive test result, I update my probability about whether or not that person has the disease, right? I would increase that probability. Now, I don't increase it to 1 because we still have false positives, right? And if I see a negative test result, I would update my probability about whether or not they have COVID, and I would probably lower it, right? Really what we're thinking about here is I'm going to look at the outcomes of this test and update my probability about the underlying true state of nature, okay? So what I'm really looking at, and this isn't from the last slide here, but what I'm really looking at is a conditional probability. Based off the outcome of the test, what's the probability that the true state of nature is S1? And the state of nature is really, it's like, do I have COVID or do I not? Those are the 2 states of nature. Am I guilty or am I not guilty? You could do a pregnancy, right? We have pregnancy tests, so pregnant, not pregnant, right? Anything where we have 2 outcomes, right? Only 2 underlying states of nature, and we can see, a positive or negative, or just 2 outcomes on the test, guilty, not guilty. We can set these up and use Bayes' theorem. So we'll pick up on this on Friday. That Learn Smart that I assigned, I said it takes 5 or 6 minutes. It's due before we start class on Friday because the latter part of it should have some information that's related to Bayes' theorem. And I want you to get somewhat of an idea, just have your eyes see some material that's related to that before we dive into it, okay? Other than that, Excel and Connect assignment due at the end of the day on Friday, so 12 o'clock at night, 11:59, I think technically. If you have any questions, reach out. I'm meeting with some people this afternoon, so hopefully if you have questions, set up a time with me. We can get that out of the way. Other than that, I will see you guys on Friday.